All right, so polar area. So what's different about polar area is we're not going to be cutting dx's or dy's. What we're going to be cutting are these d thetas. So right here, those d thetas, we're going to be cutting little wedges as they go through here, as we go through 0 to 2 pi. So if we notice, an area of a sector is 1/2 pi r squared. So our formula is going to end up being 1/2 r squared, and that's your d theta. So notice the area formula is slightly different. You got a 1/2 out in front, comes from this 1/2 right here. The pi will get picked up as we integrate, and we're cutting the r squareds in little wedges. So the first one, I want the area inside this cardioid. So I gave you the cardioid to look at. The first thing you would do is plug in theta equals 0. If theta is equal to 0, r is equal to 2, so we're starting there. So we're going to cut theta wedges. So if I go from 0 all the way to pi, I did half my cardioid, but thankfully it's symmetrical, so we can just multiply it by 2. Or we could have integrated from 0 to 2 pi and not multiplied by 2. But remember, the formula has a 1/2 and it has r squared. Often, the symmetry will make things a lot easier, but we have to be able to talk about this many different ways, because what will happen on the AP test is you're going to be matching things that they already have set up. So they might say, set up the integral that will find the area of this. And you have to set it up the way they asked you to, because it'll be multiple choice. So I'm not going to integrate these right now. They always have you integrate these on a calculator. We'll do 1 or 2 in class just to make sure, but not today. So here, they want you to find the area of one petal of my curve. And again, I gave you the graph. But what I like to think of is always keep the graph how I wanted you guys to graph them. Remember, you put the n theta, your r, your theta, and you always chose 0 and pi over 2. So when you divide by 3, half of a petal would go from 0 to pi over 6. So here's where we are at theta equals 0. At pi over 6, we've hit the max of that petal. So I can integrate that from 0 to pi over 6, r squared. There's a half out in front, but we only found the area of half the petal, so you have to multiply it by 2. Another way to do it is if we want to do the entire petal. Remember, here is telling you the important things. Things are happening every pi over 6. So here's where we are at 0, pi over 6, 2 pi over 6, which is pi over 3. So if I want to go through the entire petal, it'd be from 0 to pi over 3. Now, limit gates are always 0 to pi over 4. That will always give you half of one loop, so 0 to pi over 4. But remember, limit gates had r squared, so that's what you have right here. You do not have to square it again. But it only wanted to find the area of one loop, so using symmetry, we multiply it by 2. So here's where it is at 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Area inside the inner loop of that. So remember how this was mapped out. If I plug in theta equals 0, I'm going to start here at -2. So here's where we are at 0. We exit at pi over 3. We go all the way around. We enter it at 5 pi over 3 and finish it off at 2 pi. Remember, this is the only cardioid direction that had it starting inside the inner loop. All the other kind of combinations had it starting somewhere else. Well, first thing I have to do is decide where we come in and out of the pole. Remember, that's when r is equal to 0. So here's where we are at 0. We leave it at pi over 3. So if I sketch out and integrate that one piece, this is going to be half of one of the inside loop. So I can go from 0 to pi over 3, half of one loop. There. Now, unlike the other one where we just had it, go back and get the rest of it, like on that petal, we were here at pi over 6, 0, pi over 6, and 2 pi over 6. We can't do that because when I go from pi over 3, 2 pi over 3 is somewhere over here. It's not on the same thing. So what we have to do is go backwards. So it's really also, instead of 5 pi over 3, we can say it's the same thing as negative pi over 3. So we can integrate from negative pi over 3 to pi over 3, and that will be the entire inner loop. The area between the loops. So again, this is the same graph, so we know that we're starting inside the inner loop. So right here, you can see I'm subtracting off one loop. I'm subtracting off what the area was, the inner loop. So this was the area of the inner loop. I'm going to do this in two different colors. So first thing I'm going to do is, this is where we are at theta equals 0 to pi over 3. Then as I start going I'm going to start going over here. You notice that we're covering up, even though we're going to the big curve, we're still covering up that little one. And as we come over here, now I've gone over the middle one again. So I'm counting things more than once. Well, where do we exit the inner loop? We exit the inner loop at pi over 3. So we know right here is pi over 3. That's when we're leaving that inner loop. And I'm going to keep following that all the way until pi. That'll give me kind of the outside, including the inner loop, because it maps over that inner loop, and then we're going to subtract the inner loop. Another way we could have done this is you could have said 1/2 the integral from 0 to 2 pi of the curve, and then subtract 2 inner loops, because as you go through the graph, it traces over that inner loop twice. In here, we're asking for inside the circle and outside the cardioid. So you can see what we're talking about is this piece is right here. So when you understand how these are mapped, we got to figure out where it is at theta equals 0. So at theta equals 0, both curves are right here. So if I start tracing out and integrating from theta equals 0, it would be getting all this right here, which is not even the things that we're talking about. What we really want is between these two curves, which doesn't even start until after they intersect. So you're going to go from pi over 6 where they intersect, all the way to 5 pi over 6, and just big radius minus little radius. Big radius squared minus little radius squared. Same thing like top minus bottom, except for we're going to have bigger curve and inside curve. You could have also gone from pi over 6 to pi over 2 and used symmetry and multiplied it by 2. Kind of the same thing here. We want it inside and outside that. So we want this piece right here. So again, it's not going to start until you actually pick up at pi over 6. Then you would take the big radius squared minus the little radius squared.